Right, but that's
But
what's
when we
very
get radar
spin fires.
corrected, then yeah, the spitfires kind of won't ball wax.
I also know someone whose father-in-law was an ace pilot in World War II. He was gunning down Zeros, and one day he had 3 kills with half of his ammo still on the plane when he returned to the aircraft carrier.
Do you fly a Hellcat?
Yeah.
Yeah, that's one. Okay.
Yeah, but even with a superior airplane, most people cannot do it. With only half the ammo. With 3 kills. He was an ace pilot, and he didn't. My acquaintance did not even know about it until he traveled to London, where in the airport they had they hung one of those Hellcat fighter planes, airplanes, and it has his name on it. It's like, whoa, that's my father-in-law.
It's a little street cred.
Yeah. Yeah, the what is before the Hellcat was the Bobcat?
No, the Corsair, which wasn't very good.
Yeah, but they have the same exterior. They look very similar on the exterior.
So the Corsair had the kind of look.
Yeah, it's that.
It's not the Corsair, it's the Bobcat. The Bobcat is the first one, and then the Hellcat is the second one.
No, you're thinking of the
Wildcat?
Wildcats.
Yeah,
Okay.
the Wildcats.
Okay,
It took
but-
a while for them to get to you with the Alpha.
Yeah, but one version is much better than the other one, and the Zeros used to have a game with those to see who would stall first, because whoever stalled first turned around
The
and got
F4Fs
shot down.
maneuver against the Zeros.
Yeah, but the second version is much better, and the Zeros cannot identify which one it is, or at least not at the beginning. So they get into trouble because of that. I think the Japanese were also running out of really good pilots.
Yeah, they
Yeah,
were.
the-
They only had 2 or 3 who actually survived from the attack on Pearl Harbor to the end of the war. By the end, they just trained them how to fly. They didn't teach them how to land.
The M models were pretty good by the end of the war. They didn't have any combat veteran pilots.
But they were training kids, with have a tank of fuel and teach them how to, land, not land, but hit
crash
the
into
crash into the enemy.
bombers and the ships.
But they weren't even as effective anymore because those kids could just fly straight into it. They could not evade the
Part of the
anti-aircraft
problem was the
missiles.
Bushido code, because it was death before dishonor. Recovering their pilots wasn't a high thing because they were expected to die if they weren't accomplishing their mission.
Right.
So we had the opposite approach, where it was more important for the pilot to survive and get out of the plane.
Right.
We'd recover them with our subs, so our pilots continually got better while they were running out of qualified and experienced pilots. It was a difference of doctrine that attrition played a very heavy part of.
Yep. That also kind of sets up their expectation of the American invasion too, and that's why they were fighting so hard, to stop Americans.
Yeah. Well, Okinawa was pretty bad. We lost over 70% of our forces that went in.
Because they were projecting what they would have done to another country, they were projecting that to the Americans and thinking they would have done the same thing to them. And as a result,
yeah.
they would fight to the last person, last bullet.
Well, they were telling all their people we were enslaving them, treating them
Right.
harshly and everything.
Yep. A lot of that is propaganda. You don't see the Italians, fighting nearly as hard.
I think a lot of their officer corps kind of experienced Manchuria also, so they expected that would be the
Right.
They just
reciprocal
turn around.
response.
Exactly.
So they kind of proliferated that fear down the ranks.
Yep.
That's a good sign.
All right. Well, I guess we can move from World War II to assembly language programming. The real exciting stuff. Okay, here's your new homework assignment. You can see that this one is not nearly as bad as the other one. The program is a base conversion program. If you look at this is pure C code. I actually compiled it and made sure that it worked. We have a whole bunch of variables up here. We have a single character. We have variable x, b1, b2, and power. X is just an integer to use to store a value. B1 is the base of the input, and B2 is the base of the output. Remember, this is a base conversion program. So you're going to read a number in using one base, and then you print the number out using another base. Power, I'll show you what power is going to use, how it is going to be used later on. For testing purposes, I would use 5 as B1 and use 7 for B2. You can change this to test the program. I would use 10 and 10 first. Okay, because we are very familiar with base 10, use 10 and 10 to make sure your program works first. If it works with 10 and 10, it will most likely work with the other bases as a result. The label start your code here is here so that I can put a label and put a breakpoint here, so I can change certain things at that breakpoint, like changing the bases B1 and B2 to test your programs. So after this part, you have to implement the rest of the program. This part will be your implementation. You have to implement this too, but I can change that before I continue execution of your program in my script. The first thing is we initialize x to 0, and then what we'll do is we'll use a loop to read in a number in base B1. The first line or the repeat loop will first read a character. If read returns a non-zero value, which means I actually did read a character, it will then check whether we are reading the line feed character or not. So in other words, according to this condition, we'll be stuck in a loop as long as I can read another character and it is not the line feed character. I will not give you anything input that is erroneous, so you don't have to check for any non-digit characters or any other thing. It is guaranteed that this has to be a number that I'm feeding to your program. When you do read a single character, which is stored in CH, then what you do is you finish this computation. This computation looks kind of complicated, but it really is not that complicated. The first part is multiplying x by B1. Okay, this is supposed to be B1, not B. Let me fix that. I actually copied the code by hand from the editor, so during the copy process, I made a typo here. Because without that fixed, your program is not going to work. This is supposed to be B1. Okay, so we multiply x by B1, and then we add the difference between CH and ASCII code 0. That's because when you read a digit in from standard in, that is the ASCII code of 0 to 9. The ASCII code of 0, if I remember correctly, is 32. Okay, the digit 0, when you look up the ASCII code of 0, it has an ASCII value of 32, which is not good for computation. So that's why you have to subtract the ASCII code of 0 from CH first to convert the ASCII code to an actual numerical value. In other words, if you read in the ASCII of 5, the letter 5, the digit 5, which is ASCII code 37, when you subtract 32 from 37, you get a value of 5. Then you can use that value for computation purposes. So that's why we have a subtraction here. The multiplication, I will show you the multiplication instruction later on, so you can use the multiplication instruction in this particular case. Are there any questions at this point? Well, do we know how to do this? This is actually one of the key part of this program is do we know how to interact with the operating system? We talked about this last time. Can anyone remember what is the number of this operating system service? Is number 3. Yep, number 3 is read, number 4 is write. The 3 parameters basically go to different registers. This is in EBX, this is in ECX, and this one is in EDX. Okay. Any questions about this? It's all good? What is going to store the return value? Because this looks like we have to use the return value of the read operation. The read operation, sorry? EAX, very good. Okay, so we have talked about that in the class, and I think I still have that program from last week. So you can refer to that program when you need some clues of how to implement the read operation. When you get out of the loop, we have a number already read in base B1. So what we need to do next is to convert the number and print it out in base 2. What we do first is we have to figure out the largest power of B2 that is less than or equal to the largest number you can represent using a 32-bit unsigned number. Okay. And this will basically give you that particular thing. If I remember correctly, I have to do a UL here to force it to be a unsigned long, because when you specify constants, if you don't specify UL, it is by default a signed integer. And then it will try to use signed arithmetic for the rest of it. I want to use unsigned, so you have to append uppercase U, uppercase L in order to convert into an unsigned long type. So as long as the largest number I can represent using a 32-bit unsigned number divided by power is larger than B2, I will multiply B2 with power and store it back into power. So I keep this loop going until I find the largest power of B2 that can still be represented by a 32-bit unsigned number. That's basically what this loop is for. And after that, we can do this loop here. This loop is just saying for each power of B2, starting with the largest power, we will get the digit out by dividing x by power. But we cannot print that number out because it will just give us 0 to 9. 0 to 9, if you write it to the screen, those are all control characters. They're non-printable characters. To convert those to printable characters, we have to add the ASCII code of 0 to those particular values. And then we use the write operation. I'm being a little bit lazy here. I'm not checking the result of write. I'm assuming that it is okay to write to standard out. It's not going to have any problems. Okay. And then what we do is we also cut power down by, And then what we do is we have to handle the rest of the number, the remainder of the number. The percent symbol here is the mod operation. It returns the remainder of a division. In this case, x is divided by power, but we are not interested in the quotient. We're only interested in the remainder in this case. And then what we do is we also divide power by B2, so we reduce the power and get ready for the next digit. This has to do with the fact that when we print out a number, we print out the most significant digit first. So that's why you have to print out, this will print the most significant digit, and then the second most significant digit. When it gets down to 1, it is the least significant digit. When you divide 1 by B2, it becomes 0, so power is no longer greater than 0, and it will get out of the loop. Any questions about this? Yep.
Really quickly, at the beginning it said, was checking if the character was not equal to 10. Was it ASCII?
Well, when you read it in 10 is the line feed character, which is when you press the return key or the enter key, it is encoded as the line feed character, so it checks end of line basically. When you type a number and you press the enter key, that will terminate the loop. But if you do Control D, it will terminate the loop as well. I think most people will exit the loop because it is reading the line feed character. And then the last part here is really just print one last line feed character so that your prompt will not appear on the same line as the last output line of the program itself. Just finishing up everything nicely. All right. Are there any questions about this other than how do we do multiply, divide, and mod? No questions? Yep.
This read and write and this thing in brackets, did we discuss it last time?
Yes. Yes, we did. We talked about, you mean this operation and also this operation? Yep, we definitely talked about the read operation. Because I demonstrated the program of how to read something from standard in. We did not use a write operation. We did not have a write operation example. We can do one today. I mean, that's pretty easy to do. Instead of using system surface number 3, which means you put 3 in EAX and then you do the int $0x80. With a write operation, you put a 4 in EAX because it is system surface number 4. I can show you how to do that. That's pretty easy. All right. Anything else about this program that you want to ask before we move on and have one example of the write operation and also talk about how to multiply and divide? Yep.
I don't know what line is it, like when a character equals character plus 0?
Yeah.
And this 0 is the character?
It's the ASCII code of 0. That's fairly typical C code. Okay. Any other questions? You can use, quote, 0 quote as a literal constant too in assembly. Okay. Any other questions? Now there are a lot of interesting part of this program that is, that requires some attention. For instance, when you look at CH is a single char. It's an 8-bit, thing. But when you look at X and power, they're both 32 bits. So we are storing the quotient of a 32-bit division into an 8-bit thing. So you have to be a little bit careful, with this operation. For the most part, this is not where the problems will come from. This will be where problems can happen. Look at this Look at this operation here. X is 32-bit. B1 is 32-bit. The product is at least 32-bit. CH is 8-bit. The ASCII code of 0 is 8-bit. So on this side, we only have an 8-bit number. So now the question is, how do you add an 8-bit number to a 32-bit number and then store the result in a 32-bit number? In C, it is automatic promotion, so you didn't have to think about it in your C and C++ class. In assembly, there's no such thing as automated type promotion. In this case, you can do the type of promotion pretty easily, because what happens is, in this calculation, the result will be stored in a, well, there are several ways to do it. Okay, there are several ways to do it. One way is to kind of cheat, and just allocate more than just 8 bits here. So you basically pad it, when you allocate the bytes. But that's not a very reliable way. The most reliable way is really to do all the calculations here in 8-bit. So use the B suffix when you do the subtraction. And then what you do is you have to clear a 32-bit register with all zeros, and then just copy the result of this subtraction to the least significant 8-bit of the 32-bit register. Then you automatically have the other 24-bit being zeros. Okay, so that's a pretty easy way to do your own promotion. Okay, any other questions? No other questions? You guys are awfully quiet today. All right. Yep.
This might be a silly question, but can we just see, and I can do this on my own later if you don't want to take time, but just see an example of this program being run. I just want to know what we're going to read and write out.
It reads a number, and then it prints, the representation in the other base. Okay. But with all the leading zeros, so you will see, like 0, 0, 0, 0, 0, and then the rest of it being the number. Okay. So leading zeros will be printed, because when I write the digit, I don't really differentiate whether it's a leading zero or not. You can, it's probably not a bad idea just to copy and paste the program, and just compile it in C, and then you can interleave the code with your own code. This one is not nearly as nasty from the perspective of the control structure, because we don't have anything that's really like this long, and then you have to use the Morgan's law like 3 times to boil it down to the manageable part. Okay. Any other questions about this one? Well, when you have questions, just remember to ask me, and we'll just go ahead and move on to talk about how to do multiplication, and how to do division, and how to write. Okay, so those 3 will address all 3 at the same time. And you have 1 week to do this homework assignment.
Until next Tuesday?
Yes, due next Tuesday. Okay. So now on to the example part, the really important part. So let me go to today's folder. And let's deal with division first. I'm just going to write a very simple program to do division. Text, global start, underscore start. Okay. So what we need to do is to remember that when you specify a division instruction, now let me just show you a little bit of note that I just typed today, how to multiply and divide. So if you have any doubt about how to use those instructions, just click here and it has the basic instructions. But instead of reading this out to you, I'll just do one simple example so that you can see the result in GDB. Okay. When you use a division instruction, the dividend, D-I-V-I-D-N-D, is in EDX EAX. This means EDX stores bit 32 to 64, and register EAX stores bit 0 to 31. The least significant portion is in EAX, the most significant portion is in EDX. So the dividend is actually a 64-bit number, not a 32-bit number. The divisor is the operand of the instruction. The operand can either be a register operand or it can be a memory operand, but not an immediate operand. Not that the immediate operand would be very useful in this program. Okay, so we'll go ahead and initialize the registers a little bit. I'll put a 0 into EDX, but don't forget to do it because the instruction will use EDX as the most significant portion of the dividend. If you do not initialize it, it will take whatever EDX has at the time as the most significant portion of the dividend. So you really need to remember to initialize EDX. And then we'll put some random value into EAX just to test the instruction. And we'll just try some simple stuff like 57, put it into EAX, and then we'll have the division instruction, DIVL in this case because we have a long division instruction. And remember how the second operand, the other operand has to be a register or memory operand. We'll just put something else into another register. We'll put 12 into EBX as our divisor. So this is how the instruction goes. EDX and EAX are never specified as operands. They are implicit operands. So you have to keep that in mind too. And the instruction only has to specify who has the divisor. The dividend is understood to be in EDX EAX. Do we have any questions about the division instruction? No? Okay. So we'll just go ahead and put a no up here because I'm pretty sure I can stop the program at that point in GDB and not really have to run it all the way through. Question?
Yeah, so basically this fourth line, dval, does it divide 57 by 12?
Does that answer your question? Okay. All right, so let's go ahead and test this program. Because I still haven't really talked about, well, where are the results of the division? So we'll go ahead and put a breakpoint on line 9 because the move-L instructions are fairly, boring. So we'll go ahead and run the program up to line 9. We'll just double check and make sure all the registers have what they are supposed to have, EDX, EAX, and EBX. And as expected, EDX has a value of 0, EAX has a value of 57, and EBX has a value of 12, which means our dividend is really just 57 because the most significant portion is all 0. And then our divisor is EBX, so 57 divided by 12 is 4 with a remainder of 9, right?
Yeah.
Okay, so we want to find out, how the results are stored. I can just tell you right away, but I want you guys to kind of watch the screen and do your own interpretation. Single step through the division instruction. Look at the registers again. So what do you think? Who has the remainder?
EDX.
EDX stores the remainder. EAX stores the quotient. And EBX is not changed because it is just a divisor. Okay, so that's basically how the division instruction works. It is all written already online, so when you refer to the notes up here, it really says exactly the same thing. But I think going through GDB, to illustrate it, makes it easier to remember. Are there any questions about the division instruction? Well, even though there's no question about it, I have one tip. In the C code, there's one assignment instruction just to deal with the remainder, and there's another instruction that only makes use of the quotient. And those are two separate statements in C. But as you can see, the divide long instruction gives you both at the same time. So what you can do is to kind of shortcut it and combine two C statements into just a few assembly instructions. You only have to perform the divide instruction once, and then just put the results into different places as when it is all done. Any other questions about this demonstration? Nothing about this demonstration? Yep.
Could you run it again, but put something in EDX first? So there's something in EDX and EAX.
EDX is the most significant 32 bits of the dividend, and then EAX is the least significant 32 bits of the 64-bit dividend. So you have to initialize both registers before you perform the divide instruction.
Right, but can we just see an example of both registers having a non-zero value?
Yeah, you can change this program so that EDX has a non-zero value, but that means your quotient is going to be pretty big. So it's not going to be obvious. Okay, you can do it, but the result is not going to be obvious. You will have to verify the result using a calculator anyway. Okay, and this is a program you can change quickly to just to try it out. Okay. Any other questions about the divide instruction? Moving on to the multiplication instruction. So the multiplication instruction is very similar to the divide instruction in many ways, even though it does the opposite of what the divide instruction does. So in this case, we are going to multiply the implied operand here is EAX. EAX and EDX are both implied operands. So we'll put some values like 12 into EAX, and then we'll put another value into say EDX here. The mul instruction, just like with the division instruction, only takes one operand. In this case, I'll use EBX. The other two implied operands are EAX and EDX. EAX in this case will be multiplied with EBX. The resulting 64-bit product will be stored in EDX EAX. Okay, so the input does not include EDX, but the output includes EDX. Okay, so we'll go ahead and try this instruction out and find out what it does. Are there any questions before we move on to the command line and start the debugging?
The input was EAX, EBX every time. Is that what you were saying?
In this case, the input is EBX because I specify EBX as its only operand,
Okay.
but the implied input operand is EAX. Because you need two numbers to multiply, the operand specifies one, and then EAX always specifies the other. But the output operands would include EAX and EDX because if the product needs 64-bit to store, it would use EDX also. Well, I shouldn't put it that way. The product is always stored in EDX EAX. So if the number is too small, then EDX is just all zeros.
Can you specify two numbers to put in there, or is it always going to pull EAX? Can you specify two numbers instead of all, EBX? Can you specify two? No, you can't.
No, you
It's
cannot.
always EAX. Yeah.
It's only
I get it.
EAX and in this case EBX. Yep.
So if you're trying to raise something to a power, would you just put it in EAX and then use the mul?
You mean to raise it to multiply to itself like the square
Yeah.
of the number?
Would it just do EAX times EAX?
I believe so, yes. Okay. Now, in addition to this code here, I'll just go ahead and store something in EDX. So I'm going to store some, gibberish value in EDX. Because what I want to do is to show you that it will destroy the value of EDX, You do not count on EDX retaining its value, even though the product does not require 64 bits to represent. Okay, so we'll go ahead and try this one out. Put a breakpoint on line 7 because all the other instructions are fairly boring. Run the program, and I'm just going to lazy here. We'll take a look at EAX. It has a value of 12, not unexpected. EDX has a value of 4231, just some gibberish value that I put there. EBX has a value of 4. Okay, so now I'm going to perform the multiplication by single stepping it. And then I look at the registers again. You can see EAX stores the product of the multiplication, which is 48, which is fine. But EDX gets changed at the same time because the 64-bit product has the most significant 32 bits cleared. So that's the reason why EDX went from 4231 to 0. So are there any questions about the multiplication instruction? Yep.
Can you read this about EDX once again?
EDX stores the most significant 32 bits of the 64-bit product.
Most significant
32 bits of the 64-bit product. Because when you multiply a 32-bit number to a 32-bit number, you can potentially end up with a 64-bit number. All right. So are you guys feeling okay? Do we have all the necessary pieces here? Okay. So once again, when you write this program, do it step by step. Okay. Just I did promise that I would demonstrate how to use write. But before I even do that, I'll go ahead and take a look at the man page of write. So the write operation, the first operand specifies the file descriptor. The second operand specifies a pointer to where are you writing from memory to the output file. And the third parameter specifies the number of bytes. It returns the number of bytes actually written to the file descriptor, but in this case, I'm not really expecting any problems, so I'm not interpreting the result, the return value of the write operation. And to finish the discussion, or at least get to the resource that you should also look up, is the OS services or Linux system call table. Let me just open it up in a tab. You can see here when EAX has a value of 4, it specifies a system write operation, which is the write call that we are using in the homework assignment. EBX is an unsigned integer because it has to store the file handle or the file descriptor. ECX is a pointer, and then EDX is the size, which is basically another integer. And here onto a sample program for the write operation. For the write operation, I will go ahead and do something like this. I'll put a label L1 here, and I'll do a little trick. Okay, I'll do a little trick that will come in handy sometimes. And I'll do a ASCII, which is ASCII instead of ASCII's ASCIIZ. This is what I will use because the write operation is not null terminated. So it doesn't really make any difference whether you null terminate the string or not, because the operation itself is length delimited and not null terminated. So here I would just say assembly programming is fun, which it is. Can't remember whether I have to use quotes or double quotes. I will try double quotes first.
Does it return a value of 0? Okay, that's a joke.
Okay, so we'll have a string length here. And string length can be defined. Now this is one of the very few times where we actually use an equal symbol to define a symbol, because we are not defining a label. We are trying to figure out what is the length of the string itself. And you can do the calculation like this. Because what the dot is representing is the current location in this particular section. And this is right after I allocate for the string, assembly programming is fun. So if I take that address and subtract L1 from it, that will give me the actual number of characters allocated by the ASCII construct. Okay, so this is a neat little trick, so that you can compute, length or the displacement or offsets, amongst the objects that you're allocating. And then the program is going to be like this: underscore start. We need 4 in EAX to specify the right operation. We need 1 in EBX to specify the standard out. We need a pointer to be stored in ECX, basically pointing to where things are started. In this case, it will be $L1, not L1, but $L1, because what you need in ECX is the address, not the content at that address. And last, we need string length in EDX, because we need to tell the right operation. How many bytes are we supposed to write to standard out in this case? And of course, you can initialize all the registers all you want. If you forget to do the actual int instruction, nothing happens. Okay. So this will be our little program. With this one, there's really no need to run it through the debugger. So I'm just going to finish up the program with our usual exit code. And it should print. Assembly programming is fun. And I'll just make this, make a little improvement here by saying .by10 as our line feed character. If I don't put a line feed character where the cursor is right now, then the output of this program will be immediately to the left-hand side of the command prompt, which makes the output kind of hard to read. This extra line feed character makes sure that the command prompt itself, the prompt of the command line, is on the next line instead of the end of the output of this program. If you want, double line feed, that's how you can do double line feed pretty easily. Okay, so we'll go ahead and I really don't need G steps, but I'll do it anyway, just in case we want to go into the debugger and link the program, run the program, and it has 2 line feeds. Okay. But your program doesn't need to print multiple characters at once. Your program only needs to print 1 character at a time. So are we doing okay so far with, yep.
I just want to make sure the string length is also the ASCII. So like we don't need to redeclare it like as a ASCII type.
The string length is a label defined to be the difference between the dot, which is the current location, and the label L1, which is the beginning of the string. So it has nothing to do with ASCII at all. String length has nothing to do with whether it's in ASCII or not. Yep.
Can you explain what the .by10 means again?
It allocates 1 byte, and the value of that byte is 10 in decimal. 10 turns out to be the ASCII code of line feed as well. So basically, just 2 line feed characters in this case. Any other questions about this particular program? Do we have all the pieces? Okay. All right. Well, if you guys can think of something or questions you want to ask about the homework assignment, you can ask me during the class. But without any other questions, I will move on and talk about something that is much more interesting. Yep. No question?
It was on the which you closed right now. Like it was the line this int immediate value 0 times 80. Like not at the end of the program.
That's not integer. That's software interrupt. That's what we talked about last time.
Interrupt.
It's software interrupt. It's a very, very important concept, because we spent a whole class, last class talking about the int instruction. All right. So we are moving on to the next topic, the stack, which is the basis of calling subroutines, returning from subroutines, and then later on we'll also find out, all sorts of other stuff that is also on the stack. And that it will start to explain things that you can see in a buggy C program that you cannot explain in C, but once you understand the underlying structure of your program and how it uses memory and stuff like that, then you can start to understand how memory corruption, especially on the stack, can cause your C program to behave in very, very strange ways. I mean, program crashing is not strange, but a program that will return a subroutine that will return to a point that is not the point of origin is kind of strange. Or a subroutine modifying a local variable of some callers a few levels up is kind of strange too. So all of that stuff can be explained once we understand how the stack is used in C, in a regular C and C++ program. The first topic is the stack. I never really bothered to rewrite this portion, so this is actually going back to the quote-unquote book for this class. How many people have already understood what is a stack in terms of data structure? I know data structure is not a prerequisite of this class. Some of you. How many people know what is LIFO, last in, first out? Just a general term used in daily life, not particularly in computer science. Okay, not everybody. How many people have helped somebody or has moved yourself using a U-Haul truck? I can find people who did not raise their hand in all cases. So I guess I will have to explain what a LIFO is because, yeah. But I'll use a U-Haul truck as an example. Okay. So let's say you're packing up a U-Haul truck, and this is not just any U-Haul truck. This is a really long U-Haul truck. So you're loading up a 35-foot U-Haul truck here, and let's say in the packing process, you decided to pack all the electronics, all the delicate items first because it has a little loft area where things are kind of quote unquote better protected because other things cannot crash on it. So you put all your electronic stuff there, like your charger, your cell phone, your GPS, and so on and so forth, into the little loft area in a little protected box. And then you proceeded to load everything else, furniture, all the heavy items and whatnot. And the very last item that you put onto the truck was your bicycle. And because your truck is already loaded and it's full, so you push the bicycle into your truck, and then somebody else had to slam the door shut like right away because it's so packed, right? And then you went into the driver's seat, and ready to go to the destination, only to realize that your cell phone and your GPS are in the truck, right? Well, let's think about that term, last in, first out, okay? So which item that we have just mentioned is going to pop out of the back of the truck when you open up the tailgate?
Bicycle.
The bicycle. Great. You don't need a bicycle when you need to go travel like a few hundred miles. What you need is your GPS and your cell phone. How do you get to your GPS and cell phone in this case?
Crawl over the furniture.
Or unload everything first, okay? And that's because it is last in, first out, which is also right if you spell it out, backwards, first in, last out, okay? That's basically what a stack is. Whatever you put into the stack last, you retrieve first. Whatever you put into the stack first, you retrieve last. Another prime example of a last in, first out structure in daily life, totally unintentional, is a refrigerator. Okay, just think about your refrigerator. Let's say one day you spend the money to buy a brand spanking new refrigerator, right? Okay, so empty, so clean. So you then go borrow somebody else's Costco card and went to Costco and buy a whole bunch of stuff and stack it up, right? But Costco sell packages of like huge amounts, right? Unless you have a big family, it takes a long time to finish it. So at some point you get so sick and tired of eating the same thing over and over again that you decide to go to some other store and buy something else. And then you put it in the refrigerator and so on. So let's say a month went by and you just do the same thing every week or so. Every weekend you go buy you go grocery shopping, but you never really quite finish the stuff that you bought from Costco. So after a month, when you open the fridge, what do you see first? What are the first items that you see?
What you bought last?
What you just bought, right? What you just bought a few days ago. Not the Costco items. How do you get to the Costco items?
Grab the rest out of there first.
Yep, you have to finish everything else first, or clear out the refrigerator first. In other words, the Costco items are probably molding, at the back of the refrigerator. You probably have a little nice and beautiful mold farm, back there, mold garden, with different colors and stuff. And that's also a illustration of last in, first out. Okay. Now, in programming, last in, first out is also very, very important. And I'll explain the concept of why it is so important later on. But first of all, let's think about how a stack is going to be implemented. Okay. A stack is implemented by a stack pointer and some instructions. One is called push and one is called pop. We'll start with a discussion of a stack pointer. The stack pointer is nothing more than a register called ESP. ESP is also a part of the quote-unquote general purpose register, which means all the instructions that we have talked about so far, the move instruction, the add instruction, the subtract instruction, the multiply instruction, the division instruction, the compare instruction, they will work with the ESP register just as well as EAX, EBX, and so on and so forth. But the only reason why we haven't really talked about ESP until up to this point is we don't want to use ESP for general purpose calculations because it has a very special role, in the architecture. It is actually used implicitly by many, many instructions. What it does is the stack pointer is it should be used to contain the address of the last byte put onto the stack. If you think about the stack as a container, it can contain bytes. You can continue to put more bytes into it. You can retrieve bytes out of it. The stack pointer is always the address of the last byte that you put onto the stack. Okay. So we'll think about that a little bit here. Actually, I take it back. It is the address of the next byte to remove. But isn't that the same thing?
Yes.
It really is the same thing. The stack pointer also grows down to lower addresses. Now this part is kind of interesting because basically what it says is when your program first starts running, the stack pointer points to a high memory location. As you put items into the stack, the address will get lower and lower and lower. In other words, if you want to look at the stack as a graphical thing, the stack pointer initially may point to a high location, but as you put more stuff on the stack pointer will actually get to a lower address. So we'll talk about that a little bit too because it's counterintuitive. Most of us would think we should be growing up, not growing down when we filled up a stack, but that's exactly the opposite of how it does it. Now the stack pointer can also be used as a bookmark, because what it means is this content here. Let's say the stack pointer is pointing to this location. Everything from the location that the stack pointer points to up to the boundary, the initial boundary, that's all in use. That memory content is actually in use. Everything that is below where the stack pointer is pointing to is unused. So this part is unused, and that part is used. Okay. All right. So that's a general discussion of the stack pointer. And before we go any further, we can just go ahead and go to one of our rerun one of our programs like mul here. Now multiply has nothing to do with the stack pointer at all. All I want to do is to put a breakpoint on say line 5 here and show you what the stack pointer looks like, or the value of the stack pointer. This is a pretty high value, okay? BFF F5B0 is a pretty high value. As you put more items onto the stack, you will see this value go down, not go up. Okay.
Is
there a physical reason for that, or is it
Yes,
just a-
there's a very good reason why that is the case. Okay, the next concept is called pushing and popping. Pushing and popping are basically to push a value on the stack is to store something in the stack. To pop something from the stack is to retrieve something from the stack. Okay, you can just look at this, using your kind of conventional view of what a stack is. So I'm just going to grab a pile of paper from my folder here. Okay, so I have a quote unquote stack of paper on the table. Okay, let's say this table is the stack. Initially, it is empty. To push an item on the stack is to do this. If I want to push another item on the stack, the first item is still on the stack, but then I have one more item on the stack. If I push again, I have yet another item on the stack, and another item, and another item, and so on. What pop is not to go and find out which one I want to retrieve, because the pop operation always retrieve the last item that I push on the stack. And then it will retrieve the second last item, and then retrieve the third last item. And you can intermix push and pops, so you can retrieve a few items, put a few items on the stack, retrieve a few items again, and so on. The key is you don't specify the order because it is implied by the fact that it is a stack. When you put it onto a stack, it is always on the top. When you retrieve, you're always retrieving the last item that you put on the stack that has not been retrieved yet. Are there any questions about the push and pop operation of a stack? Just abstractly, because the stack concept is not only used in assembly language programming, it is also used in computer science a lot.
So you're saying that you cannot go and retrieve something from the middle?
That is correct. It is not random access.
Even though the last is the address and you can add values to that address?
Well, you can peek into the stack using a random access method, but when you store and when you retrieve, it is always using the last in, first out order.
But you can't like we were doing, address the address.
You can peek into a stack. But when you peek into a stack, you're not popping because you're not actually retrieving. You're not moving the stack pointer.
Okay.
Okay. So there's a difference between the peeking into a stack versus retrieving an item from the stack. Yep.
Say if we were to pop 2 items off, where do those go? Where are they stored?
Very good question. When you pop something, when you retrieve something from the stack, do they just disappear into thin air, or where do we put it? In the context of assembly language programming, when you pop, you typically pop those into registers or a memory location. In other words, you remove it from the stack and then you copy it into a register or a memory location. Okay, very good question. Yep.
In reference to the stack pointer, it says contains address of the last byte put into stack or the next byte to remove.
Yep. They mean exactly the same thing because of the last in, first
So my
out.
interpretation of that is if I put a piece of paper down, ESP is right here, so it's the only thing in the stack. But then if I put another piece of paper on top of that,
ESP moves.
is going to be on the second page.
Yep. Yep.
So that what you drew on the board there is confusing to me because it looks like the ESP is moving down.
It does. It is moving down.
So it's always on the first page then?
Because you're always.
They add it to the bottom. It's
They add it to the bottom?
Yeah.
Okay.
Yep. Okay. And the next one talks about the push instruction. So this time we are talking about an actual instruction. You can see when I talk about the actual instruction, I use a fixed size font. The font is slightly different from the one before. The push instruction expects one operand, and you can use any operand. You can use immediate, you can use memory, you can use register. Okay? Whatever that operand specifies will be quote unquote stored in the stack. Okay? It's just one instruction. You don't specify exactly where to store, because of the behavior of the stack itself. You're always storing it into the stack, and the stack is a general container, so you don't get to specify exactly where or the location where you store it. You just say, oh, store this on the stack. Let's not worry about push F and push A for the time being, and we'll go ahead and skip to the pop operation. The pop instruction also expects one operand. It can specify either a register or a memory location, because what it does is it retrieves a value from the stack into the specified operand, and then the stack becomes smaller. In other words, the pop operation is not really just reading from the stack, it is also changing the size of the stack so that it is smaller. Okay? So let's go ahead and just do some experiments to find out how push and pop works.
The push operand needs register or memory operand, or can we use immediate operands for
With pop?
Push?
With push, yes, but not with pop.
Okay.
Okay. So we'll go ahead and do some experiments with this particular pair of instructions. Yep.
It makes the value of stack smaller or value of operand.
Say again?
It makes the pop makes the value of operand smaller or the
No,
value
it makes
of
the stack smaller. The push instruction makes the stack bigger because you're storing more things into the stack, and the pop instruction retrieves stuff and remove it from the quote-unquote remove it from the stack. So we'll go ahead and do some experiments here just to make sure that we understand the whole idea of push and pops. We'll start with something like this: push, let's say 23 as a long integer, and then we'll pop it into %edx, and we'll we'll just say that this is the end of the instruction. I don't even bother to finish it with the usual exit code because we're going to run this in GDB. This program is not going to show anything other than in GDB anyway. But before we run it in GDB, what do you think is the behavior of this program? The first instruction says, let's go ahead and make a copy of the value 23 and store that value in the stack. The stack gets a little bit bigger because we are storing 23 on the stack. The second instruction is going to quote-unquote pop the last item stored on the stack into EDX. So it's going to do two things. First of all, it will go to the stack and say, oh, what is the last item on the stack? It copies that to the operand, in this case is EDX, and then it will decrease the size of the stack because that item is now retrieved. It is no longer on the stack. So what do you think is the net effect of these two instructions?
ESP will be the same at the beginning.
EDX will get the value 23. Okay. So let's go ahead and see if that is really the case. And this little sample program is going to be reused again to illustrate the actual mechanism of push and pop. So we call this push pop. And I forgot to put a no op instruction, so the push instruction cannot be. I cannot stop the push out instruction. We can only stop at the pop out instruction. Oh. Cannot access.
Did you run the program yet?
No,
Yeah.
but I should be able to put a breakpoint before I run the program.
Maybe you should put in small notes.
You can just put in a, late, yeah, just put in something else to break on.
Say again?
Why don't you just put in a breakpoint? Or
Put in another no op so you can put in a breakpoint.
No, that's not. But that's. I don't think that's it though. Did I forget something? Underscore start in text section. Put a breakpoint on line 6. Nope, it's complaining about the same thing. I have to be missing something that's obvious.
Try breakpoint on 7 because you added 5.
Say again?
You added one line, so it's not 6, 7. It was 7. You wanted a breakpoint on 7.
Okay, that's fine. Let's try that. Put a breakpoint on line 7. Nope, doesn't let me do it. It's having a problem mapping the line numbers back to the memory address. So I think the assembly options are specified incorrectly. But I don't see any problems here. And then the linking is fine too. That is really mysterious. Looking at the file size, they look kind of normal. Looking at the file, I don't see anything.
The exit code didn't work.
No, that wouldn't change anything. Because we are not even close to that point yet. Okay. Link. Put a breakpoint on line 6. This time it does. So the exit code, it's really odd. That is really, really odd. Because we wrote a program without the exit code already. Yep.
What happens if you do a push L and then a pop B? What will it return to you?
It doesn't have a pop B, interestingly. Pop only has pop W and pop L. There's no pop byte. Well, that is interesting, but to understand the behavior of that, we have to understand the actual things that's going on. So let's finish this one first. That's a very good question. We'll definitely get to that part. Okay. All right, so we have a breakpoint on line 6. We'll run the program. It stops at line 6. And we'll just go ahead and take a look at EDX first, just to make sure that EDX does not start with a value of 23, because otherwise the program would not have illustrated what it is supposed to illustrate. Okay, the push instruction, single stepping through the push instruction, doesn't do anything at all to the registers except to ESP. Okay, but this time I'm not going to show you how ESP is getting changed. This time I only want to show you the effect of the push and pop instruction as far as the operands are concerned. We're not interested in the mechanism of the push and pop instructions. Not yet, not at this point. Right before the pop instruction, I want to double check that EDX does not have a value of 23, so that when we single step and check again that EDX has a value of 23, we know that is the effect of the pop instruction. Yep.
There's no way to see what's in the stack.
Yes. But we'll do that. Okay, we'll do that next. Okay, so this one, it kind of shows you what the stack is supposed to behave. We push something on the stack, we retrieve it, and and it works. Okay, so now we'll go ahead and change the program just a little bit to make it more fun. So this time we'll push another value on the stack. So 23 is one, 131 is the other one, and we'll have another pop out instruction here to pop into, let's say, EBX. Okay. All right. This time it gets a little bit more complicated. You push one item, you pop it into another item. It's just like move, it's just like copy, right? No big deal. But when you push 2 items on the stack and then you have 2 pop instructions, then now the question is, who is going to get what?
Mirror.
It's a mirror. It's because of the last in, first out nature. The last item that we push on the stack is retrieved first. So that means EDX is going to have a value of 131, and that means EBX is going to retrieve the first item that we push on the stack, which is 23. Yep.
So when you put items on the stack, they lay on top of each other like this, and then when you go to retrieve them, it comes down like that?
Correct.
Okay.
Yep. Except you look at the stack upside down. I'll explain the upside down part later. Okay.
Imagine they have Velcro in their stickers. Is that better? Yeah.
Yeah, just looking from the bat's perspective, everything is upside
So
down.
you got your
Hey, can't look.
Okay, assemble, link, and GDB. Okay. So this time, I think I'll just go ahead and put a breakpoint on line 11 just to confirm the result of the program. So I'm not going to single step through the program. So run the program. We're now stopping on line 11. We'll take a look at EDX, which is supposed to be 131, and also EBX, which is supposed to be 23. And sure enough, those are the values in these two registers. So that means you can use push and pop to swap values of two registers. You push EAX, you push EBX, but then when you pop EAX and then you pop EBX. That will swap the values of two registers. Kind of tricky, kind of nifty little tricks you can do with the stack. Are we still doing okay so far with the concepts of pushing and popping?
Is there something between the values he's put in, like a null terminator or something?
Null terminator?
Just to distinguish one from another, or is it
No, that's the part. You were asking a question that is related to what he asked a little bit earlier about what if we push long and then we pop W? What is going to happen in that case? Well, before we get there, let's go ahead and this time we take a look at ESP, and we'll also take a peek at what exactly is on the stack. Can we see what exactly is on the stack? Can we use the debugger to gain an X-ray vision on the stack and see actually what is happening when we push and pop? So we'll do the same thing, the same program. We don't need a new program for this purpose. We'll put a breakpoint on line 6 first, okay? And we'll run the program. Now we are right before the first push instruction. But this time, I'm not just going to run through the program and look at the end results in EBX and EDX. This time, I'll take a look at ESP as well. This is before the first push instruction. I take a look at ESP. It has this kind of long gibberish value, but we'll keep an eye on it, okay? And then we'll single step the program, okay? Single step. So the push immediate 23 instruction has now executed. We'll take a look at ESP again. Oh, is it bigger or smaller than before?
Smaller.
It is smaller by 4 bytes. By 4 bytes. Because these are all in hexadecimal. This is a 0, and C represents 12 in hexadecimal. So we are actually, it has decreased by 4. Does it make sense?
Yeah.
Did we store a 4-byte thing on the stack? We did. Okay, because push L, says it has to be a long thing. Yep.
So would this hexadecimal number be the size of the available stack?
No.
It decrements when you put something
Yeah,
on.
but the other end of the stack, the other extreme of the stack is not location 0.
Okay.
It's somewhere, but I cannot remember exactly where.
Okay, so that just points to where the stack starts. So
Yes. Well, no. Remember what the stack pointer points to? It points to the very last byte that I have pushed on the stack. Now, that is useful because that means if I use the X command to display at this location, I should see what? What should I see?
23.
I should see 23 as a 4-byte thing. Okay, let's do that. So we'll do a X slash, it's going to be a 32-bit thing, so I have to use a word in this case. And we'll go ahead and use X to display in hexadecimal. Well, it's up to you. We'll do it in several ways. And $ESP refers to the value of registered ESP, so we'll use that to supply the address. And it's 17 in hexadecimal, which is 23 in decimal. But exactly how are these bytes arranged? Because I'm only displaying this whole thing as a 32-bit thing. So what if I display that as 4BX? In other words, I display it as 4 individual bytes. What do you expect? Tell me what you think. 17000000, because it is still following the rules of Little Endian. Okay, so let's go ahead and take a look, and we just confirm that. Very interesting. Now we are ready to single step the other push instruction. The other push instruction is push 131 in decimal. So now let's go ahead and single step through the instruction. And the first thing we'll do is to take a look at ESP. What do you think will be the last digit, the least significant digit of ESP right now? We just pushed another item, another 4-byte item on the stack. What is C minus 4?
No idea. 9.
C is 12. 12 minus 4 is 8. Okay? So it should be the same, all except the least significant digit should be an 8 now. Okay? So let's double check. And sure enough, that is the case. What is it pointing at? What is the stack pointer pointing at? The very last byte that we pushed on the stack. But we didn't push just 1 byte, we pushed 4 bytes. So I should be able to look at it the same way as before. And what do you think I should be expecting when I do this? I should be expecting 131 represented as a 32-bit number, but printed using the little endian convention. The least significant byte is printed first. That's exactly what we're seeing, because 80 in hexadecimal is 128 in decimal. So when you add 3 to it, it becomes 131. So it all adds up. Okay. Do we have any questions at this point? But what about that thing that we pushed earlier? Is that still on the stack?
Yeah.
Let's find out. All we have to do is to change, instead of printing 4 bytes, we print 8 bytes. And you can see the 23, it's still on the stack. That's how the push instruction works, okay? It actually does 2 things. One is it will store, the first thing it will do is it will decrement the stack pointer by the size of the operand, or the size that you're specifying. So when you have push L, it decrements by 4. If you have push W, it decrements by 2. Then it will go ahead and store the value. It will just do a move, implicit move instruction to move the operand to the location on the stack. Okay, so it's actually 2 operations combined as 1. Now we are down to the first pop L instruction. What do you think the pop L instruction will do now that we understand the stack pointer, how it works, and we also know what the stack pointer is pointing to? What do you think the pop L instruction is going to do? It doesn't really get rid of anything. It moves the stack pointer. Okay? Remember, the stack pointer is a bookmark to indicate one side is in use and the other side is free. Okay? So all we are doing is we're moving the bookmark. We are not erasing the pages as we go. All we are doing is moving the bookmark like 4 bytes earlier. So that means after the pop L instruction, what can you expect in ESP? ESP right now is ends with an 8.
Right, go back to 59C.
It will go back to C, and as a result, let's go ahead and single step through the instruction. IR ESP, and sure enough, it becomes 59C again. And what about the content originally at that location? In other words, if I explicitly go to this location, what am I supposed to find here? Well, that's a trick question. It's a trick question because there are things that I cannot illustrate. I'll just type it BFFF F598. Hey, it's still there.
Garbage.
No, it's still the same content as before.
The pointer is no longer pointing at it.
The pointer is no longer pointing at it. Exactly. So it's not exactly garbage, but it is still there. Okay, the content is still there. The next question is, yep, go ahead.
Okay, I can understand in real mode that would be guaranteed to always be the case, but anytime we've got like time slicing in our operating systems, do we guarantee that lock on that memory, or could another process come in and change that memory?
What you just said is definitely interesting because it is something that it has to do with something that we have talked about already last week. Okay, this location is still here because nothing is coming here to mess up the stack for us. Okay, this is the only program running, and nobody else is supposed to touch this part of the stack. And that's because we are not running in real mode. It's because we are running in protected mode, and the operating system has its own stack. In other words, at this time here, when I'm stopping and just talking in GDB, tons of interrupts are happening. Okay, timer interrupts are happening, network card interrupts are happening, DMA interrupts are happening, and so on and so forth. Now, all of those things actually use a stack, because remember, when you have an interrupt, right before you go to the interrupt surface routine, what do you need to do? You need to save the location where it is interrupting. To where? On the stack. But we are not seeing any changes here. This stays the same the whole time. It's only because when you have a protected mode operating system like Linux or Windows NT and so on, interrupts would use a system stack and not the user stack. And that's why your stack is not messed up by interrupts happening all the time in the background asynchronously. You cannot predict when it happens. If you use any type of system that has no operating system and you have to write everything, then you cannot trust the fact that this content will still be there, because in those cases the interrupts or the interrupt mechanism would save the return value to the free portion of the stack. This portion is now considered free. In other words, you cannot be guaranteed that this content will continue to be there once you get past the pop instruction. But I cannot really show you the fact that it can be changed simply because we are running in a using an operating system that shields that part from you. Yep.
You've alluded to there being more than one stack. You said something about a system stack. You
Yep.
said something about an operating system stack.
Yep.
And a user stack.
Yep.
Sounds like a user stack is reserved for
Just
regular programs.
this process.
Just this process. So every
Just this
program
process.
that
Every
is running
process has its own stack.
has its own stack. Okay.
Now, you can actually push that argument one step further. In programming concepts, every thread has its own stack.
That makes sense.
So not only with every process, by the time you get to programming using multiple threads and stuff like that, each thread has its own stack too. Yep.
So I've heard people use the terminology kernel space and user space. Is this what they're talking about? Or?
This is a part of that. Basically in kernel space, the stack that the interrupt surface routine will be using is in system space or kernel space. And that's why it doesn't touch the user space stuff here, and your program doesn't get the return address saved onto this stack here. Okay. Now that part is very important. We'll talk about it again when we get to that point. Yep.
At this point, if you look at the 8 bytes of ESP, it's shown like a 0, 1, and a bunch of zeros. What is that?
Aha. Okay. So basically what you're doing is you're running this command again. But first of all, should we be looking past the 4 bytes?
I can do that.
Okay. How much of the stack is stuff that we pushed in this program at this point? We have already popped once.
Right, so 4 bytes.
Only 4 bytes are the stuff that we pushed using our own code. So if I run this, that means these 4 bytes is the stuff that we pushed in our own program. The other 4 bytes will be stuff that is pushed by something else. The loader is probably responsible for these bytes. In fact, I can probably guess what that is. I'm thinking this is probably argc in C programming, the number of arguments passed to the command line itself. If you don't know what I'm talking about, that's fine. It's not a big thing. Because we ran this program without any additional arguments, and there's always one being the program name itself. So that's why it is a 1.
So if there were multiple command line arguments, is that probably what the linker
Yes.
would insert
In other words, if we run it with blah, 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 that number will probably change. In fact, where this is before we push. Now, before the first push instruction, what is going to be at ESP? It will be the last thing that was pushed before we get control of the program. Okay? So let's go ahead and take a peek and see what it is. So we'll go use x/4bx $ESP, and this time it is 5. Let's count and see whether 5 makes sense. 1, 2, 3, 4, 5. So that really begs the question, if I display 8 bytes, what do I get? What do you think that is? Look at the other 4 bytes here. What do you think it looks like? I think it looks like another location on the stack. Right? Because it seems like the stack pointer is always saying BFFF, F blah blah blah. Okay, so if you read this number, this is little endian. Remember, this is also in little endian format. So this is actually BFFF F6DB. So it seems to be specifying another location on the stack. What do you think is at that location? Well, let's track it down, okay? Because you will find it pretty interesting, because as you track down these pointers, okay, we'll just go ahead and look at 0xBFFF6DB, and it shows you, something that looks like. What does it look like to you? Do you see a pattern to it? 2F, 6.8, 6F, 6D. They look like ASCII code to me. Okay, because anything that is within this range, can be printed. The lowest number that is printable is 20, which is the space character. The highest one that you can quote unquote print is, I think, 7F or 80. Anything beyond 80 are not printable in ASCII. So this looks printable to me. So that really asks me, that is begging me to use, is begging me to use the other option, which is to display it as characters. What do you think we'll be seeing here? No idea? /HOM.
Home directory.
Yes. This is more like a Wheel of Fortune now. Right? Okay. So let's display a little bit more. Home/US ER. Okay. Do you think there's more to it?
I think so. I think it's the whole directory.
/2 today's folder. Very good. And today's folder has 8 characters to it, and then plus CIS, the underscore, and then cisp310. So that's another 16 characters. Okay. And sure enough, we have cisp310. Okay. So, and then what else do you think is on this, in this string here?
The program name and then the command line.
The programming and then the. Well, just the program name, actually. I think it is just the program name. Yeah, it's just the program name.
Where are those arguments? Where do they?
Okay, I'll show you where the arguments are. Okay. Okay, so to show the program name, it is just, this one is called what? Push pop?
Push pop,
So plus 7 or 8 more, to account for the last, the slash and also the 0.
So 34.
So 30, no, we need more than that.
That would be
40. Just go overshoot it.
Yeah, do it.
Okay, so we have /home/user/20120313 underscore CISP310 /PUSHPOP and then a null terminator. That's what it is. So your question is, where's the rest of it? All that gibberish that I added. Well, let's backtrack a little bit here. We have just looked at this item, right? What do you think is beyond that item?
Right after it.
Okay. In other words, we want to use ESP plus 8. Okay. So let's do that. X slash. Now, since we already know it's a 32-bit address, we can just be a little bit kinder to ourselves and use WX here. ESP plus 8. Oh, that looks like an address to me.
Isn't that it poking out after the old terminator? ASD.
Yep. It is, but this pointer is also pointing to that location. And what do you think? It's plus 12, the next argument. And then we have 5 of these things. So this will be, this is the second, the third, the fourth, and finally the fifth. This is how arguments that you pass on the command line, that you type on the command line, are passed to a program. Okay? And this is also why, when you specify main in a C and C++ program, what is the type? How do you specify the parameters of your main function? Just void, right? Most people just put a void in it. But you know what? When you need to interpret the arguments passed from the command line, what you do is to say main has 2 parameters. One is int argc, which means how many arguments there are. In this case, there are 5. The second parameter is a const char asterisk argv angle brackets, which means the second parameter is an array, is a pointer to an array of pointers to strings. What did we just see a little bit earlier?
Arrays.
Argv.
Pointers to strings. Yeah.
Yep. Because we have each one of these is a pointer to char, which is a string. But when you look at this thing as on its own, it's an array of pointers, and each pointer points to a string.
That's what would happen if you looked at the memory content at these addresses.
Yeah, exactly. We can do that pretty quickly. So x slash.
You would find the arguments again and ask for characters.
Yeah. And we can just type one of these things in, BFFF F704. That's the J. And let's display multiple items. Yep, that's the gibberish that I typed. Yes, I remember exactly what gibberish I typed. Okay, so but that really, that's really giving you an insight of how the stack is used. It's also giving you an insight of how dangerous it is when you're running your program and you have full access to the stack, because you're not only responsible for the stuff that you push on the stack, but if you overpop, you can actually destroy stuff that somebody else's before you push on the stack. Okay? Now, when you look at a program like this, it's like, well, it's no big deal. We're just, trashing, the command line options and stuff like that. Yep.
The operating system doesn't protect something like that?
Because that's all a part of your process.
Okay. I guess I don't, when is the operating system, I don't know how operating systems work, but it would make sense to me that the operating system might know where various pointers and stacks are, and then if you try to access a memory location,
it does that to a certain extent, but the granularity of that protection is pretty big chunks. Okay, it cannot protect smaller chunks. It can protect bigger chunks. The entire stack is considered one big chunk. Okay. Now we are running out of time today, but you should read ahead of me, because ultimately the call and the return instructions for subroutine call and subroutine return, they are using the stack as well. Okay, so you can kind of imagine what can happen when you have a subroutine and inside you have some push and pop instructions, but instead of the right kind of pushing and popping, it is not balanced. You're either pushing too much and popping not having enough pop instructions, or having too many pop instructions compared to the push instructions. Your stack becomes unbalanced. And if your stack becomes unbalanced, very strange things can happen. Okay, so we'll a lot of mysterious stuff will happen from now on. Before today, the first 8 weeks of the class, I would consider that pretty plain and boring. Now is where the fun begins.
On that note, can you upload our lectures for the last 3 weeks?
Oh, you mean the files?
Yeah, well, I tried to look them up last week when I was still working
mean
on the last one, and I couldn't find anything later than the 13th of February.
The files or the bits?
The YouTube.
The YouTube?
I didn't think so.
I couldn't find something on YouTube.
Okay, I thought I uploaded, stuff, like, already.
May I make a suggestion?
Okay, well, I was looking last week, so.
Okay. Let me double check. Yep.
When you intend to abstract the stack with an analogy vertically, it becomes all counterintuitive, and it's really useful to flip it on its side, and something that analogizes well for that is like a napkin holder. And then that way you can still do the last in first out analogy while kind of maintaining the intuitiveness of the Western left to right. And that way you still have memory aligning.
In fact, that will also align with how I teach CISP300.
Yeah, so just...
Remember in CISP300, we use the columns, we allocate, and then we deallocate and allocate again? Push them up, push them up.
Yeah.
Very good.
Side, much more intuitive.
All right, thanks.
I was just waiting for you to confirm whether you're coming.
So I'm going to go to my channel because I thought I uploaded everything. What'd you get on the exam? At least.
Yeah, because the latest I could find was like just before our exam in February, which wasn't anything current. Huh?
It came with one license. One license was allowed to be installed.
Do you see any 310 stuff? That's old.
Today's the 7th.
Okay. No, today's the 13th.
13th?
All right. When did you?
It would have been last
See, it says
class.
views 1 day ago. 1 day ago, you only just did it. Yeah, like I said, I was looking
uploaded
last
over
week.
The weekend, I think.
That's why. Okay. All right. Thank you.
Yeah, sure.
I was just curious, you said the operating system protects to a certain degree the stack from the user programs. So like it wouldn't protect user programs from trouncing each other, maybe, but would it like
The programs cannot trash each other because they all have different stacks, and those stacks are in protected spaces.
Okay.
So each program has its own stack, but they cannot touch the stack of other programs, other processes, I should say.
So the push-pop dangers really come when you try, like when you add something to the stack and then deallocate it and then add, and then you might end up popping something that you added a long time ago or something like that.